So, welcome back to week 4 of our AIMS club. Today we will dive deeper into matrices, their operations, and their crucial role in AI and machine learning. Matrices are fundamental to how AI algorithm process and understand data. So grasping this concept is essential for anyone interested in AI. But before we start, I'd like to mention that we are friendly and inclusive space. And so let's encourage each other and lift one another up. This session will be recorded. So let's start. In this session, we will start with the basics, defining what matrices are and how we represent them. Then we'll move on different types of matrices and how to perform basic operations like addition and multiplication. We will also explore the properties of these operations. Crucially, we will see how matrices are applied in various AI fields, such as neural networks, computer vision, and it's going to be a comprehensive journey throughout the world of matrices in AI. So let's begin by understanding what exactly a matrix is. Simply put, a matrix is an organized way of arranging numbers, symbols, or expressions in a rectangular grid. Think of it as a table of various values. It's defined by its rows and columns. And as you can see in the visual representation, we have elements arranged in horizontal rows and vertical columns, enclosed in square brackets. For instance, matrix A here is a simple example with 2 rows and 3 columns containing numerical values. Matrices are not just abstract mathematical objects. They are fundamental structures for sorting and manipulating data, especially in AI. Now that we know what a matrix is, let's talk about how we write and refer to them. We typically use uppercase letter to name matrices like A, B, or X. The size of matrix is described by its dimensions given as M by N, where M is the number of rows, horizontal lines, and N is the number of columns, vertical lines. Each entry with a matrix is called an element. We use a lowercase letter with subscript to denote elements. Aij refers to the element located in the ith row and the jth column. Looking back at our example, matrix A is a 2 by 3 matrix because it has 2 rows and 3 columns. And for example, the element in the first row and first column, A11, is 2, while the element in the second row and third column, A23, is -1. Understanding this notation is crucial for working with matrices. Matrices come in various types, each with unique properties. A square matrix is when the number of rows and columns are the same. Think of it as a square grid of numbers. If the number of rows and columns are different, we have a rectangular matrix, like our example matrix A. The identity matrix, denoted by I, is a special square matrix. It has ones along its main diagonal from the top left corner to the bottom right, and zeros everywhere else. Identity matrices are crucial in linear algebra, similar to the number 1 in regular multiplication. Lastly, the zero matrix, denoted by 0, is quite simple. All its elements are 0. These different types of matrices have specific role and behaviors in matrix operations and applications. When do we say two matrices are the same? Matrix equality is quite strict. For two matrices, say A and B, to be considered equal, two conditions must be met. First, they must have the same dimensions, that is, the same number of rows and the same number of columns. Second, every corresponding element in both matrices must be equal, meaning the element in the first row, first column of A must be equal to the element in the first row, first column of B, and so on for all elements. As you can see in the example, matrices A and B are equal because they have the same dimensions 2 by 2 and all corresponding elements are identical. However, C and D are not equal because they have different dimensions, and E and F are not equal because even though they have the same dimensions, some of their corresponding elements are different. Now let's start discussing matrix operations, beginning with addition. The fundamental rule to remember is that you can only add matrices if they have the exact same dimensions, that is, the same number of rows and the same number of columns. When you add matrices, you do it element-wise. This means you take each corresponding element from the matrices you are adding and sum them together to get the element in the same position in the resulting matrix. If we call the matrices, we are adding 1 and A and B, and they are sum C. Then each element in C, denoted as Cij, is simply the sum of the corresponding elements Aij from A and Bij from B. Let's look at a quick example to make this clear. Here we have two 2 by 2 matrices, A and B. To find their sum, A plus B, we add the elements in corresponding positions. So, the top left element of the result is 1 plus 5 is equal 6. The top right is 2 plus 6 and is equal 8. The bottom left is 3 plus 7 equals 10, and the bottom right is 4 plus 8, which equals 12. As you can see, matrix addition is a straightforward operation when you understand the element-wise rule and the dimension requirements. It's also associative, so when adding 3 or more matrices, the way you group them doesn't change the result, and the zero matrix acts as the additive identity, meaning adding a zero matrix to any matrix A levels leaves A unchanged, just like adding 0 to any number. Now let's move to matrix multiplication, which is a bit more complex than addition. The most important rule to understand about matrix multiplication is about the dimensions of the matrices you are trying to multiply. If you want to multiply matrix A by matrix B, the number of columns in matrix A must be equal to the number of matrix B. If this condition is not met, you cannot perform the multiplication. If matrix A has dimensions m by m rows and n columns, and matrix B has dimensions n by p, n rows and p columns, then their product, let's call it C, will have dimensions m by p. Notice how the inner dimensions n and m must match, and the outer dimensions m and p determine the size of the resulting matrix. So, how do we actually calculate each element in the product matrices when we multiply two matrices? If we want to find the element in the we use a specific formula. This element Ci is calculated by taking the ith row of matrix A and the jth column of matrix B. Then you multiply the corresponding elements in the row and column and sum up all these products. The formula shown here, Cij equal sigma Aik by B Ij for k equal 1 to n represents this process. The summation symbol sigma means we are adding up a series of products for each values of k from 1 to n, where n is the number of columns in A and rows in B. We multiply the element Aik from the ith row and kth column of A with the element Bkj from the kth row and jth column of B. Summing up all these products gives us the element Cij. To help visualize this process, imagine we want to calculate a specific element in the product matrix. We focus on the row in the first matrix, matrix A, and a column in the second matrix, matrix B. We then mentally slide the row across the column, multiplying the first entry of the row with the first entry of the column, the second entry of the row with the second entry of the column, and so on. After multiplying each pair of corresponding elements, we add up all these products. This sum is the value of the element in our product matrix, located at the intersections of the row we choose from matrix A and the column we choose from matrix B. We repeat process for every row of matrix A and every column of matrix B to fill out the entire product matrix. Let's break down the process. To find the element in the ith row and jth column to the product matrix C, you look at the ith row of matrix A and the jth column of matrix B. You multiply the first element of the row with the first element of the column, the second element of the row with the second element of the column, and so on. Then you add up all these products. The sum becomes the element Cij. Let's work through a concrete example. Here we are multiplying a 2 by 2 matrix A by a 2 by 3 matrix B. First, check if multiplication is possible. Matrix A has 2 columns and matrix B has 2 rows. So yes, it's possible. The result will be a 2 by 3 matrix. To calculate the element in the first row and first column of the product, we take the first row of A, 1, 2, and the first column of B, 5, 9. We calculate 1 by 5 plus 2 by 9, which equals 23. For the first row, second column, we use the first row of A, which is A1, 2, and the second column of B, which is 6, 10, getting 1 multiply 6 plus 2 multiply 10, which equals 26. And for the first row, third column, we use the first row of A, which is 1, 2, and the third column of B, which is 7, 11, and resulting in 1 by 7 plus 2 by 11 equal 29. We repeat this process for the second row of A, which with each column of B to get the second row of the product matrix. This step-by-step calculating demonstrates how matrix multiplication works in practice. Before we start working with matrices in Python, we need to introduce NumPy, uh, which stands for Numerical Python. It's the foundational library for almost all numerical and scientific computing in Python. At its core, NumPy provides powerful support for working with large multidimensional arrays and matrices. It also comes packed with a vast collection of mathematical functions optimized to operate efficiently on the arrays. For linear algebra and AI, NumPy is absolutely indispensable. Why is NumPy so crucial for AI? Several key reasons. First, efficiency. NumPy arrays are implemented in C, which makes numerical operations incredibly fast compared to using standard Python lists. Secondly, vectorization. NumPy allows you to perform operations on entire arrays at once without writing slow Python loops. This vectorized approach leads to significant speed improvements. Third, NumPy is the foundation for almost all major Python-based AI and machine learning libraries. Libraries like TensorFlow, PyTorch, and scikit-learn are built on top of NumPy. Finally, it provides all the essential linear algebra tools we need. For AI, we have handle massive amounts of data and complex computation. NumPy's efficiency and capabilities are not just harmful, they are essential. Now let's talk about Jupyter notebooks. We'll be using Jupyter notebooks for all our Python coding this week because they're perfect for learning, especially when you're just starting out. Jupyter notebooks provide an interactive environment. You write and run code in cells and see the output immediately, making it easy to experiment and learn step by step. So, best uh, of all with Google Colabs, you don't need to install anything of your computer. You just run Jupyter Notebooks directly in your web browser. Notebooks let you combine code and explanations in one document, which is great for understanding linear algebra concepts alongside the Python code. They are ideal for step-by-step learning and are the industry standard in data science and AI. To get started right now, just go to colab.research.google.com in your browser and sign in with a Google account. You'll be coding in a minute. So let's get started with NumPy in Jupyter Notebook. First, open Google Colab and create new notebook by click this blue button. In the very first code cell of your new notebook, just type import numpy as nmp and press Shift plus Enter to run it, or Run button. This imports the NumPy library and makes it ready to use. Now you can start creating matrices and vectors using NumPy functions in subsequent code cells. The key is to experiment. Change the code to rerun cells and see the result right away. This interactive approach is the best way to learn. Try typing in the example code shown here in a cell and running it to create your first NumPy matrix in Jupyter Notebook. Okay, and let's get hands-on and create some matrices in our Jupyter Notebook. In a new code cell, type this code. It shows you how to create different types of matrices using NumPy, a basic to the matrix. A matrix with floating point numbers, a matrix filled with zeros using NP zeros, and a matrix filled with ones using NP ones. And please actually type this code into your CodeLab notebook and run each code cell. See the different types of matrices that are created. Experiment by changing the numbers, dimensions, and functions like NP0s and NP1s. Observe the output in each cell. These direct interactions is the most effective way to learn NumPy matrix creation. Let's quickly recap what a matrix is. As we discussed, a matrix is simply a rectangular arrangement of numbers in rows and columns. For example, here a 2 by 2 matrix, we define matrices by their dimensions, rows by columns. Matrices are fundamental for organizing data on linear algebra and AI. And now, in your Jupyter notebook, take a moment to create a few matrices of different sizes and with different numbers using NP array. This hands-on practice will solidify your understanding of matrix structure. Let's perform matrix addition and subtraction in Jupyter notebooks using NumPy. In a new code cell in your notebook, type this code. We import NumPy, create matrices A and B as NumPy arrays, and then perform addition and subtraction using plus and minus. Go ahead and type this code into a code cell in your code notebook and run it. Observe the resulting sum and different matrices printed below that cell. Experiment by changing the matrix values and rerunning. See how the element-wise operations work directly in your notebook. Now, we move to matrix multiplication, which has a more specific rule. Remember, to multiply matrix I by matrix B, the number of columns in A must be equal to the number of rows in B. Matrix multiplication in Jupyter notebooks with NumPy is also straightforward. In a new code cell, type this code. We create NumPy arrays for matrices A and B. We use this symbol operator for matrix multiplication in NumPy within the notebook. Type this into a new code cell in your CodeLab notebook and run it. See the resultant product matrix. You can also try np dot AB in another cell. Both do matrix multiplication. Experiment with matrices that fit the dimension rule. What happens if you try to multiply matrices with incompatible dimensions in your notebook? Try it and see the error. Learning from errors is part of the process. NumPy's vectorization power is best seen in action. In a new Jupyter notebook code cell, type and run this code. It's the same efficiency example as below. Now ready for you to run in CodeLab. You'll see a huge time difference between NumPy's vectorized addition and slower loop-based addition. Run this in your notebook and witness the speed difference yourself. This interactive demo in Jupyter makes the efficiency of NumPy and vectorization very clear and impactful, showing you why it's so important for handling large computation in AI. We've learned the basics of matrices and how to work with them in Python. Now let's see how these seemingly abstract mathematical objects become the driving force behind many of the AI technologies you encounter every day. Matrices are not just theoretical concepts, they are the fundamental language used to represent and process data in diverse AI fields. Matrices are fundamental to AI, powering key areas like neural network, computer vision, and machine learning. Let's see how. So, weight matrices, and this beautiful image from 3 blue 1 brown transformers, how LLMs works, explained visually video, and I'll share it with you later. It's super exciting video. You should watch it. So, and weight matrices crucial in neural networks, and they store connection strengths between neurons and are adjusted as the network learns. Matrix operations, especially multiplication with weight matrices, are core to how neural network process information. As you progress in AI, you'll be working with weight matrices extensively, and you'll be able to use your Jupyter Notebook skills to design, analyze, and debug neural network components. In computer vision matrices are how computers see images. A digital image at its most basic level is a matrix of numbers. Each number represents the intensity or color value of a pixel. For a grayscale image, it's a 2D matrix. For color images, it can be a 3D matrix with height, width, and color channels like red, green, blue. Many image processing techniques like blurring an image, detecting edges, or rotating an image are achieved throughout matrix operations. For example, applying a blue filter involves convolving a small matrix, the filter kernel, across the image matrix. Convolutional neural networks, which revolutionized image recognition, are named so because their core operations is convolution, matrix-based operations, and the filter in CNNs that learn to detect features in images are themselves matrices. Computer vision literally transforms visual information into matrix manipulation. NLP uses matrices to represent text, word embedding, document term matrices, and transformer networks all rely on matrix representations and operations for language understanding. Matrices are essential in enabling computers to understand and process human language in natural language processing. One key technique is word embeddings. In NLP, we need to convert words into numbers that computers can process. Word embeddings do this by representing each word as a vector, essentially in one matrix. A collection of these word vectors for a vocabulary forms a word embedding matrix. These embeddings capture semantic meaning and relationship between words. Document term matrices are another example used in the text analysis. They represent collections of documents as matrices, showing the frequency of words in each document. Even in the most advanced NLP models, like transformer networks that power state-of-the-art language models, matrix operations are the heart of the attention mechanism that allows the model to understand context and relationship within the text. NLP relies heavily on matrices to convert and manipulate textual information numerically. In summary, matrices are truly the language of AI. They are ubiquitous, appearing in almost every area of artificial intelligence. They provide a remarkable, powerful, and efficient way to represent complex data, whether it's image, text, neural network connection, or data sets for machine learning. Matrix operations are not just mathematical abstractions, they are the actual computational engines that drive many AI algorithms, allowing them to process information, learn patterns, and make intelligent decisions. NumPy in Python gives us the practical tools to harness the power of matrices in AI development. A solid understanding of matrices is absolutely crucial for anyone who wants to build, understand, and advance the field of AI. So, continue exploring linear algebra, keep practicing with NumPy and Jupyter Notebook, and delve deeper into how matrices are applied in your specific areas of AI interest. The journey into AI is built on this foundation. So, one more thing before we wrap up, I want to make sure everything and everyone is clear on how well be running these sessions going forward. Every Sunday we'll have a short online event, just like today's session. These events will introduce the necessary materials for the following week's learning. So please mark your calendar for Sundays. Also, Discord channel. We've set up a Discord channel for ongoing communication and support. Every week, I'll introduce a homework assignment in Discord channel. This will be a list of required exercises and readings that you'll need to complete during the week and, importantly, before the next online session on Sunday. This will ensure that everyone comes prepared and we can make the most of our time together. The homework is designed to reinforce the concept we cover and give you valuable practice. So please make sure you prioritize completing it each week. It's essential for your progress. I'll add all articles, videos, tutorials used on this session in comment under this video on our YouTube channel and in Discord. Also, homework will be shared at Discord channel. So until then, our session will be recorded. And thanks everyone for being together in this session. Until then, we will finish our session. So